is yours.
Okay, fine. So thank you very much for the invitation. I'm really sorry I can't actually be with you in person. I want to tell you a story that I think most of you heard some of. I still think sometimes it's useful to try and collect it together from the top down rather than from the bottom up, which is in any case somehow the theme of rough path theory. It's a work of a great many people, and I've been privileged to stand at the edge of it and watch all of these things happen. Okay. So stream data is a slightly complicated concept, but it's something that's actually with us everywhere. It's not particularly well characterized by any particular mathematical formalism, or at least it wasn't. And it's characterized primarily by events happening in an order where it's quite clear that some things happen after other things. I think it's fair to say, actually, that the human subconscious and maybe even animal subconscious are sometimes extremely good at understanding these things, that event A happening before event B is a completely different concept, potentially, to the other way around. But unlike number, which is also obviously something very intuitive and fundamental to us, I think it is much more recently that mathematics has started to be able to really get hold of the concept of the order of events. So I've illustrated on the left the evolution of Chinese handwriting on the screen of a mobile phone, and on the right, a list of different ways we might think of stream data. Once we've understood the idea of a piece of text being a stream data or an electronic health record, we then also realize that we often want to study not a single stream, but a collection of streams. We also realize, and I want to emphasize that not every stream is stationary or even close to stationary. I mean, our lives, human lives, are a stream, each one of us, and yet no one would suggest that what happens between the age of 70 and 71 is the same as what happens between the age of 3 and 4. I think that's quite important because a lot of the stochastic literature tends to think much more in terms of stationary, randomly evolving systems. And although we've not yet made it completely mathematically precise, there are some pretty obvious core questions that one would like to be able to solve. One is that you have an ensemble, which we could call a corpus of knowledge, a language model, the behavior of human beings in terms of their health in a large database. And given all that information, this measure on streams, we might have a new stream which we've only partially observed, for example, me up to my 71st birthday. And one would like then to predict the distribution of how my life will evolve from now on, given what's happened already, and given our experience with other people. It's a very generic problem. It's actually a problem which, if you think about it, ChatGPT and these methods from large language models actually solve in a practical sense. Another thing one might really like to do, and I'm going to try and give you an application of this second one later in the talk, is one might take a large corpus of streams. Again, they don't have to be stationary. They could be things like lives. And then identify in a principled, dimensionless way what it means to be an exceptional stream, an outlier. And you might want invariance properties. Streams obviously have certain invariance. If we have a collection of paths and we want to identify an outlier, that sounds a plausible idea. But what should happen if we do some sort of linear transformation of our data? Should we have the same view of what is an outlier? What should happen if we prepend our streams, so we take account of our order structure, by a standard envelope stream, a sort of an initial kernels or something. Would we still also have the same view of what is an outlier? There are various invariance properties that you can ask about vector streams and about streams in general that can be fed into these questions about anomalous streams. But they're very fundamental questions which you can ask at a hugely abstract level. And I think the natural tendency has been to focus back on the particular examples. People analyzing literature tend to use literary methods. People analyzing electronic health records tend to analyze numerics. And actually what we tend to do is we tend to use our domain knowledge to make progress. We haven't to date really used raw mathematical knowledge. And I think the reason for that actually is that multimodal data, multidimensional, many channels of information, actually is an incredibly high dimensional problem. So high that it's quite unlikely that you're ever going to have enough data to reasonably sort out one option against another, unless you are relatively abstract and clever. So in practice, we tend to do Fourier analysis on each coordinate, one-dimensional ones, but we're not very efficient at understanding how to integrate what's going on in multiple channels mathematically. And I'm going to come back to that. But I'm going to try and get you to realize or agree with me that there is actually a sound way of trying to understand a stream that's anonymous or indifferent, at least in the early stages, to the particular perspective one comes from, whether it's healthcare data or astronomical data. And that is that the thing that we tend to be interested in about a stream is its effects. Its effects on other nonlinear systems, or maybe self-interactions, but let's not go that complicated. And we have a way of modeling effects. It's called calculus. Going right back to Newton, we have a language that allows us to explain, I think it was called interaction at a distance by people like Newton, but I'm not a historian of mathematics, to explain interaction between one evolving system, the planet, say, and another evolving system, say, be the moon. And it's called a controlled differential equation. It's amazing, actually, that Newton really did all these things because he had differential equations with solutions that weren't closed-form functions long before all the arguments about whether Fourier series could give you solutions, because we didn't know how to name the functions. It's amazing that he was doing all these things. So Newton gave us, and of course it's been profoundly important, the methodology of controlled differential equations, a way of describing the interaction between one evolving system and another. But there are limits to Newton's methodology, and the most fundamental of them really is that in many high-dimensional systems, or involving many particles or whatever, the interactions are not really smooth on normal scales. In fact, they're very non-smooth on normal scales. And of course, in this room, we have no difficulty understanding that in the 20th century, there was a massive sequence of events in mathematical terms that allowed us to make progress in this space. Of course, the most fundamental one was probably Kolmogorov, who actually allowed us to make probability into mathematics. And then Dubé allowed us to understand stochastic processes rigorously. And at the same time, Ito allowed us to understand stochastic differential equations. An amazing achievement. And so we suddenly had controls that were not other things of the same type as the thing we were looking at, planets and so on, but they would look more like noise, more like Brownian motion. And of course, Brownian motion is not differentiable. So suddenly we had this class of differential equations that weren't differential equations because they used Brownian motion. But actually, with hindsight, Ito gave up quite a lot to make this work. Basically, he exploited, as we understand, previsibility, and the key thing that he gave up was the notion of a solution on a given path. The solutions were elements of L2, and by definition, you modify a function in L2 on a null set, it's the same function. He gave up the pathwise understanding of the solution. Of course, there are various ways to fix that, but it's quite a fundamental issue. And he also, or one can prove, to Bisher and people, had a framework that sort of stopped at the world of semi-martingales. And there were lots of examples, actually, to show that this isn't quite right. I remember in the early 90s, I was doing numerical stochastic differential equations. And one thing that struck us was when you used Ito's approximation of Brownian motion, these things existed pathwise. They certainly were not almost sure concepts. But in the Dirichlet forms world, there were lots of examples of interesting processes that in some sense were integrals, but were not semi-martingales. There were lots of examples around. Anyway, rough path theory sort of found a significant answer to this problem and allows one to understand controlled differential equations far more generally, and indeed not stochastically. And the key idea was really this idea of a controlled differential equation. So the key reason for doing it was examples like this one here. This is a typical example of a stream. Things moving. There's a definite time scale, but they're not semi-martingales, not in any sensible way. They are at some very fine level, but they're not on a normal practical level. Conditional expectations are not important. But you can translate them into relatively low dimensional paths. And Mohammed Ibrahim, who is currently in number 10 as an advisor, but he was very able to take the video data and turn it into like streams of events. You know, cart is in this position and this position and this position, then turns right and goes out the video. So there's lots of data, important data, that we'd like to understand that looks a bit like a stochastic process, but it certainly is not reasonably modeled by a semi-martingale. In this particular case, we were trying to understand the relationship between the car movements at the TfL cameras, of which are about 400 in London, and the levels of nitrous oxide around London, and get better explanations of what was causing them. So the idea was that somehow we're going to understand our stream not using the methodology of Kolmogorov and Doob and time series, which focuses on a value at a time. You remember when you learned about measurability with Kolmogorov? It was all about gates and where something was at a given time. It's all about values at times, understanding the graph of your function. Actually, this is what turns out not to be the right way to do it. The idea of a screen is that you don't try and do that. Rather, you focus on its effects. Knowing the time it is where is a bit like painting a picture of the thing. We want to feel it. We want to understand its effects. Turns out that this is actually really much, much more practical approach to solving and understanding the data, because you can understand the effect on simple core systems, and you don't have to tunnel down to the very, very fine time steps. You can integrate in a nonlinear way all the fine oscillations and still get something quite useful on a coarse scale. So that actually is the key to rough path theory. It is to imagine that on some very fine scale, your data is still perfectly reasonable and bounded variation. So what you mean isn't ambiguous, but then to understand how to describe this complex oscillatory data on more normal scales, what you do is you let it control a nonlinear system. And the key of rough path theory is you don't need to let it control any system. It's enough just to control certain rather stereotyped systems. And you don't need to control them perfectly. So long as you know broadly how they behave over intervals with the right analysis and the right algebra, then that's actually going to be sufficient by taking limits to tell you what happens all the time with every system. It's a quite different way of looking at the data. But when you really stop and think about it, it's the way human beings work, for sure. An interesting and reasonable stream is a movie. How many people come out of a movie and describe it by trying to say where everything was in the third frame of the movie and where everything was in the fifth frame of the movie and the seventh frame of the movie? It's not at all what we do. We let this stream influence us, affect our emotions, and we give short reports on the different ways that it controls nonlinear systems impacted on by the movie or by our perception of the movie. As I said, the great thing about this perspective is that it also gets over the fact that I don't have to tell you about everything. I do not need to work from the bottom up. It's patently clear again from our own human experience that we do not do that. We could not do that. That is, in fact, exactly the limitation that makes it only possible to look at things of finite length, because things of finite length are the only ones where you can really look at them everywhere in a reasonably meaningful way. So the key is actually to describe it over intervals, ST, by looking at controlled systems driven by our stream. And the control system to look at least initially, but there are other sensible ones into unitary groups and so on, is the simple exponential function, except fully non-commutative. And there is the first trick and the first pain for a probabilist. Because if the path gamma is in a vector space, then there is no multiplication. So how can we do things like the exponential function? Well, the tensor product is a useful concept here. So the idea is, if you imagine that the vector space in which gamma lives is spanned by letters, then you can consider the vector space spanned by words, including the empty word. And we represent the empty word by 1. Then actually, this differential equation now makes good sense. If I have a word, I can multiply it by a letter to get a new word, one higher length. I can extend that to be bilinear. I can make a perfectly good linear differential equation like this. I can even truncate it by only looking at the words with at most k letters. So I can get these graded subfamilies. And I can do that in extraordinary abstraction. The only caveat is what to do if gamma has jumps. And gamma often will have jumps. The simplest thing to do is to fill in the gaps with straight lines. That isn't necessarily the right thing to do. And actually, the main point is that you need a modeling decision. This is not an analysis decision. It's not a mathematical decision. It's a modeling decision. What happens to your system when the driving signal jumps? Sometimes you won't know. Other times you'll have quite strong views. But once you've decided that modeling decision, you have no trouble translating this stream of information gamma into a series of higher and higher responses, depending on how many letters in the words we consider. And that's quite exciting because it's very, very abstract. It allows us to describe streams without worrying whether they're healthcare streams, people on street streams, financial streams. Now, in the end, you probably need to go back to the context, but the story of rough path theory is there is actually quite a lot to do before you get to that point. And the point is trying to take advantage of its ability to tell you how to behave before you get stuck into the actual practical aspects. But it's important before one gets actually too bogged down in everything to realize there are limitations. Signatures are a mathematical idea, just like real numbers are a mathematical idea. We're not trying to, they have implications for data science, but we're not trying to say that you have to use the signature. We're trying to say this helps you understand what you are doing. And it's sort of obvious, actually, that understanding multi-stream, multi-channel data is an extraordinarily high-dimensional problem, as I just mentioned. Most of the time, unless in natural language processing where you've got a corpus of normality, you clearly do not have enough data to do anything sensible without reducing the dimension. Signatures, actually, as we'll see later on, do reduce the dimension quite a lot, but there's still an enormous dimension. And so in lots of practical problems, will revolve around ways to reduce that dimension further. And we should not be worried about that, afraid by that. We should understand signature is a mathematical object that can give us insight into the other objects, rather than thinking it is always the solution. The work in developing rough path theory has always been a very collective one, and there have been lots and lots of people played really crucial roles. The solution to that differential equation that we were talking about is now called the signature of the path. It was first really studied by Casey Chen, and an important paper was the paper by Ben Hambley and myself, where we showed that it uniquely characterizes the path up to a generalized notion of reparameterization. And Horatio and Geng and Danyu and myself then went on to show that the same theorem was true, almost exactly the same way for rough paths as well as ordinary bounded variation paths. The signature has many, many different features. It's a bit like looking at the Laplace transform. And in particular, the expected value of it more or less characterizes the distribution of the measure on these paths without any Markovian structure. So it's a sort of replacement of the martingale problem when you don't have a view about the behavior of the paths and you're not claiming they're Markovian. It's still very, very active. We heard from Antoine a little bit about signature kernels. These were introduced by Harold and oh, my name slips me offhand, but anyway, Harold and his colleagues. But one of the exciting things about them, from my perspective, is that it turns out that they solve a PDE. And you can solve this PDE on the GPU. And so you come back from the signatures and rough paths to solving PDEs driven by the paths, and you never need to know about signatures or tensor algebras in order to do kernel type statistics on these stream data using this PDE, which people did not know before for this purpose. More recently, Maud Lemercier has transformed this story, because the original story only worked if the paths had bounded variation. It did not cope with paths that were complex and had highly oscillatory, so speech or any of the real world data, which actually typically does not have on normal scales of bounded variation. And what Maud and I discovered is that actually you need a new PDE. Depending on how rough the path is, the PDE gets significantly more complicated, but it's still viable. But you still have a kernel tree. You still have a PDE. It's very exciting. Chris Salvi, who's out there somewhere, has this amazing paper with Rosa and Jeremy and Yosha, really describing the algebra of understanding an independent collection of functions on streams, so that if you're really trying to understand a stream, there's always going to be some functions that can be derived from other ones. So it becomes a seriously interesting question to understand what are basic sets of functions that give you the information, and what are the functions that are simply polynomials in these. Well, that actually has a good theory. It's still got some open questions, but it was exciting to me that the Journal of Algebra was interested in publishing that paper. So now I want to focus very much on the data science. Streams are everywhere. Functions on streams are things we really want to understand, right? One stream could have been the handwriting on the mobile phone, and the function will be turning it into a character. Another one could be a patient in hospital, and you're reading their measurements and looking at them and all the rest of it, and you'd like to understand that they're in danger of getting sepsis. Again, this is a function on a stream. An investment in finance is no different, right? In that case, the stream is the prices of the traded assets, and your function is your trader who is doing his investment strategy, and you're interested in understanding those investment strategies, and in particular choosing good ones as opposed to bad ones. So functions on streams are a really core element of data science. But from a mathematical point of view, we'll see that a very rich class of them can be understood using this signature. As I try to explain, the signature takes its values in the space spanned by words, which is an algebra. We multiply two words together by concatenation. It doesn't take a generic element. They are very specific subspace of this algebra. In fact, it's a homomorphism. Concatenate two streams and their signatures multiply. It also has inverses, because if you run a stream backwards, you get the inverse. So the target is a group. So taking the signature as a feature set that takes your data into a group inside the tensor algebra. And it's been very well studied for a very long time. As I just explained, it's a faithful map up to reparameterization of the path. One way to get functions from this picture is to take linear combinations of the coefficients of the words. So to take an element of the dual space of this tensor algebra. They, when restricted to these group-like elements, produce real-valued functions. That's obvious. What's less obvious is that when I multiply two of these real-valued functions together, I can actually find a new linear object that is their product. And this was first understood by Ree in 1958 and is important in combinatorial topology. And it is actually given by something called the shuffle product. The product of two dual words is actually the riffle shuffle of them. It's all possible ways of interleaving the two packs of cards. So it's very well understood. It's quite expensive to work out, but it has a very important consequence. The linear functions thought of as functions on signatures of paths are an algebra. and abelian algebra. And that means that you can apply the Stone-Weierstrass theorem. If you do that in a Neuritz paper, you're quite likely to get referees saying, what is all this junk I've never heard of? Which says more about our undergraduate curriculums than anything else. But still, we understand that the Stone-Weierstrass theorem tells us that if we have a compact set of paths, compact set of streams, then actually we have an algebra of functions on that compact set. It's easy to see that it separates the signatures. It's easy to see that it contains the constants. So it's going to be uniformly dense. So there is a universality. So the signature unwinds this nonlinearity. If you have a polynomial function, then if you're willing to go higher up in iterated integrals, it becomes a linear function. And that's actually really quite helpful, because how do we fit curves to data? We do it by going finding a representation where the polynomials of low degree are linear, and then doing linear analysis. And it's exactly the same here. It means that we can now explore functions, at least locally, on paths or streams, and we can explore them by taking linear regression. Importantly, it's not all functions on streams, right? It's all functions on unparameterized streams. But that can be even more helpful, as I'll try to explain later on. And here is typical real-world data. On the left is actually patient signs from mimic data on intensive care units. On the right is actually mood data scored by individuals, of one mood against the other in each of these little squares. And we want functions on these. On the left-hand side, it was indeed the function of trying to understand the onset of sepsis. On the right-hand side, it was really trying to understand the subgroup of the population the individuals were drawn for, because this data was actually made out of a group of 3 groups of people. One group had a diagnosis of bipolar, another had a diagnosis of borderline personality, and the third had a diagnosis of normal. And it was very successful at separating. And it was very successful on relatively low dimensional sets of data, because the signature offers this graded low dimensional series of functions that you can use, a bit like polynomials, but in a way that is structured towards stream data. But if you don't have much data, you don't try and use many of them. So I would like to be a bit radical and say, we can go the other way. These are actually little movements that all represent tracks of ships moving for a short time. But also, they're all elements of the tensor algebra. And I think you should be able to take them into Algebra 1 and persuade people that, this is a better way of thinking about elements of the tensor algebra than an abstract piece of algebra. And actually, this data we're looking at here was one of the initial examples when we started trying to look at the problem of anomaly detection I talked about earlier on. There's an error here. That should be 2023. The original version was in 2020. Because the fact is that there are good ways of constructing methodologies for detecting anomalies against cohorts of normality. In this case, we did it with small ships and big ships quite successfully. And the key to these approaches is that you're testing against a cohort of normality, but you can choose what is normal. You don't have to treat it as given to you. And this is incredibly powerful because you can use it in all sorts of ways that people would not imagine. On the right, was work where Chris actually played an important part, which is actually using the logs that come from monitoring processes in a computer to produce trees of paths. But these are event logs, basically. Saved a file, got an internet connection, allocated some memory, logs of events. But the point is that actually in a computer, you don't have one process. The process spawns sub-processes, and they spawn sub-processes. You actually end up with a tree. And these are some of the trees, the channels you're looking at in the trees now. But by looking at the individual branches to the leaves, you get paths or streams, and then the whole collection is an ensemble of them. So you can look at the expected signature, and this can give you an exchangeable description of the tree as a nice vector that you can then use in your statistics. So again, it was a powerful way to encode what was previously really quite complicated data in a way that's pretty tractable, in which you can use signatures and kernels to make good progress. I don't know how we're doing for time at this point. Yeah, okay, that's fine. So what I tried to tell you so far is that rough path theory allows you to introduce a set of tools and understandings that can be applied to streams. You think of the stream through its ability to influence simple nonlinear systems, that's called the signature, and then you can study these objects. And there's a lot to study and there's a lot to access before you get down to the domain specifics. And to do this, you actually need computational tools. One of the basic problems is that sitting inside the tensor algebra is the Lie algebra of this group I was talking about. And this Lie algebra removes all redundancy and is a very useful object, and we get to it through the log signature. But there is no canonical basis for this Lie algebra, even though there is a canonical basis potentially for the original tensor algebra with our letters. Understanding this computational complexity caused by the Jacobi identities is a real issue that induces some proper serious mathematics, all bases and so on. You cannot really do manipulations in this space without some serious mathematics. Initially, we all focused on the signature, and there are several packages out there that will do things. Probably these days most commonly used is Symmetry on PyTorch, that's a bit dated now, and now Signax, written by a Korean mathematician, which works on JAX. But all of these focus on the signature. Actually, if you're going to make progress in machine learning and things, you need to focus on functions on paths as well as on data. In other words, you need to understand the shuffle products and the dual objects, not just the original data objects in the tensor algebra. And you also need to understand streams as objects. And by that, I mean a stream is an object that you can query over an interval and get its effect on simple nonlinear systems. So in other words, you can compute the signature truncated over short intervals. And to try and overcome that, Sam Morley has, over the last 2 or 3 years, but now it's finally there, been creating a toolbox called Roughpy, which if NumPy is aimed at matrices, Roughpy is aimed at stream data from rough path theory. And it now exists. And I'm going to show you a little bit how you can use it. It's not the end of the story by any means, because to make these things really work well, you've got to have differentiation, you've got to have everything working smoothly on the GPU. And unfortunately, it's not just a question of using jacks, because the objects here have very different structures and dimensions to the simple matrices that you see in linear algebra. But anyway, that's clearly something we need to do right now. But I thought I'd give you some examples of this. So we now have, I think, a good package, and we're beginning to use it seriously, as I will explain as well. I thought I'd try and give you some indication of how it's used and going. So Roughpy is a Python-based tool. You just pip install it. And one of its most fundamental objects is a stream. So here we're talking about data from something called the Dale dataset, which is actually 5 student houses with their voltage and current recorded 16,000 times a second for 3 to 5 years. So it's the voltage and current coming into the house. There's lots of other data as well. And that's what we're going to talk about here. So as you will know, electricity data has a cyclical behavior. The external mains goes around either every 50th of a second in the UK, every 60th of a second in other parts of the world. So the first thing we do is we just create a stream. We work out where we're going to put it, and then we just create a stream from that data. The data is actually, in this case, recorded in a sound file. It's two-dimensional. It has a current and a voltage. We're going to work it out to, say, depth 6. So that means we're going to work out signatures up to level 6 when we're asked for them. We're going to work over the reals. We could work over polynomials to get formulae. And we're going to decide how finely we want to look at our data in terms of time. And then we can just do things like get the log signature or the signature over an interval, how much we want to round so that we make certain the intervals are compatible and join up with each other. And it will do all these other things I was telling about too, about half shuffles and shuffles and so on. So here, we plotted the data over a 50th of a second, and it goes round in a circle, roughly speaking. We've chosen our interval, which is a dyadic interval of length 1/50th of a second. And we simply get back the first few terms in the log signature using this whole basis that I told you about. And so there we are. We produce from our complicated path over a 50th of a second. With no great fuss, we produce a 1, 2, 3, 4, 5-dimensional feature set, which gives a meaningful description of what this electricity was doing over this time. Here's the code that would more or less actually do it. We set up the data, we define the stream from the data location, we query it over an interval. We're only looking at depth 3, even though the original thing was worked out to depth 6. And now we're visualizing it by simply plotting the increments, not the higher order things. Suppose, though, we wanted to visualize the higher order things. So this will be each of these points, each interval in time, each of this 50th of a second would have associated with it a point in 5-dimensional space. So now we're going to switch from understanding it over the 50th of a second to understanding what happens 1/50th of a second to the next. Then we can use the fact that we put this thing into a 5-dimensional space. We can use standard visualization programs like UMAP to take the different possibilities for what could happen over a 50th of a second. take their representations in terms of these 5-dimensional vectors, and then find a way of representing them through some nonlinear map that's more understandable using our data. And that's what we're doing here. You can take data over a couple of 100 seconds. You can look at all of these 10,000 or so different cycles in 5 dimensions. You can use standard but amazing manifold learning type code to represent this data down into 2-dimensional data. And you can check it does a reasonable job by splitting the data into 2, learning how to describe the data with 1 bit and seeing how it describes the remaining data. And you'll see it does a reasonably good job. In fact, it does an excellent job. And in this way, with almost no effort at all, and just using Roughpy and standard tools from modern data analysis, we found a way of encoding our cycles into a relatively low-dimensional family of possibilities. So if we want to determine, for example, which device was on, was it the washing machine, was it the dishwasher, and so on, this will give us a far better chance, and a quite principled chance too, of working out the right sort of answers. So that's telling you a little bit about the software Roughpy. But in the remaining few minutes that I have, which aren't very many, I'd like to just take you through some of the current applications that are going on. I'm going to take you very quickly through why signatures. I'm going to say something very quick about kernels and a couple of things about how they're applied. And I want to keep within time. At the moment, it's 19 minutes past, so my guess is I have about 7 minutes. So I'm going to go quite quickly. Right, so the reason a signature is a good idea is, as I've said before, multimodal data is incredibly high dimensional. A lot of that high dimensionality comes from a symmetry, and that symmetry is if I sample the data at a different rate, if I reparameterize it, this is a group action that often does not change the curve at all. It really doesn't matter if I'm measuring my journey from London to Edinburgh when I sample it, but each way of doing it is a sort of different parameterization. And data science hates symmetry because it means different data with the same meaning, and it's got to learn that they're the same. Well, learning reparameterization is a huge group, and you're not going to succeed. The signature exactly filters out that symmetry. Exactly. It removes that symmetry completely. It still leaves you with an exponential pain, but it's a much, much smaller infinite exponential pain. And that is why it can reduce the problem to tractable low-dimensional problems that are informative. Yeah, I don't want to spend very long on it. The signature gives a way of talking about the complexity of the path on a certain scale without ever going down to the detail of it. And that's actually an incredibly valuable thing to do. And it's easy to see that actually it's orders of magnitude more efficient, even for Brownian motion. If you have Brownian motion and you describe it by its values at times, then a famous result of Martin Clark tells you this works incredibly badly to describe a path, describe solutions to the path. That's why we have Levy area. That's why we have second order methods. But what we see now is that people are, Andreas and JG, have these new generative models that actually will give you a Brownian motion and its Levy area. So actually will generate a real two-dimensional second order rough path. So this is going to fantastically change simulation because it means that you can actually solve the differential equations accurately. without any approximation. But the one I wanted to spend most time on briefly, because I think we've done some, or Maud has done some incredibly exciting work recently, is on kernels. It's easy to see that even for rough paths, well, maybe not easy, but it's true, that even for rough paths, the coefficients in the kernel decay factorially fast. But there are exponentially many of them. So the way it works is that up to a certain point, the exponential wins. And then from then on, the factorial wins. But that means we can always take inner products of two kernels, of two signatures, because eventually the factorial wins against the exponential explosions. And so there's a natural inner product on paths in a vector space with an alpha, with a basis given by channels or an alphabet. And so the game is to compute it. And as I mentioned, Chris and co-authors identified a PDE that works if the paths are bounded variation. And here it is. And it's a fairly well-known PDE, and it has a good numerical approach to it, and you can solve it on a GPU efficiently, and it's a great kernel trick. But it's quadratic in the length of the paths, and that's really quite bad news. But what Maud has realized, and it really comes from understanding a homogenization of these problems, is that when you go to rough paths, it's not even true anymore that the kernel is obtained by solving the PDE. It's actually solved by solving whatever you would get from homogenizing this PDE. And it turns out that when you homogenize these hyperbolic PDEs, you get a new PDE with new data, new state variables. And those state variables can be worked out. There's a lovely new PDE, and you can find it in the archive paper. Doing it rigorously is really quite serious, but it's doable. And you get a new kernel trick and a new PDE. Remarkable thing is, using Roughpy, you can actually solve this PDE, write it down very easily, actually. It's set up for it because it does all the shuffle products and the adjoints and things. It's actually really easy to do. So that's really exciting. So there is now a viable tractable kernel method for working with much more complicated data. The outliers have been very successful. One of their uses has been actually in detecting noise in astronomical data. Turns out that in radio telescopes, one of the biggest problems today is figuring out when your data is no good because somebody switched on their car. Telescopes get more sensitive, human beings create more noise. Figuring out when the data is meaningless is actually a really, really important question. Up to now, the main methods for doing this have been model-based, looking for the kind of noise you want. But using the anomaly-based methods, using signatures, you can go the other way. You can take a corpus of normality and notice when it's not normal. Turns out that this is actually quite a lot more sensitive without throwing up false positives. So this is the one that actually uses the signatures and the anomaly and the corpus-based semi-supervised anomaly detection. And I'll just finish off with this one, which I think is also very important. Signatures are very high dimensional. So you would think they couldn't be used for very high dimensional data. But you'd be wrong. Because modern high dimensional data science has things like BERT, word embeddings, which actually take your stream and convert it into a Markovian stream by adding information, which sounds the wrong way. But once you have a Markovian stream, you can do what I was doing with the UMAP before. The Markovian stream, you can map it in a one-to-one way non-linearly down onto a low-dimensional stream. It's still the same Markovian stream, providing that map is one-to-one. It only needs to be one-to-one on the range of the paths in this huge dimensional space. So you can project, in this case, speech, so not speech, social media messages, down onto a 10 or 11 dimensional space using one of these visualization programs. And then you can analyze the signatures of this highly oscillatory 12-dimensional data, and you can do very well. Okay, that's it. I wanted to talk about neural CDEs as well, but I haven't got time. That's it. Thank you very much.